etc. He authored 4 books and around 400 research papers. I think I won't read all the bio because it's too long. Maybe let's switch directly to the main topics about embedded systems, discrete event modeling and simulation for development for embedded and real-time systems. Thank you for
Okay, let's see how this works. Can you hear me? Yes. So good morning. Thank you for the invitation. It's a pleasure to be here. So today I'm trying to move a bit from performance modeling simulation to what do we do next with all of that, right? So in our lab, we work on different topics related to discrete event modeling and simulation. My presentation today is about how to use discrete event modeling for development of cyber-physical systems, embedded real-time applications embedded in their environment and their environment. For years now, the embedded systems, cyber-physical systems have been growing in popularity, and they are complex, heterogeneous, and you have hardware-software application mixed with the physical environment that they have to control. They normally are devoted to a specific function, okay? And the hardware and software are tightly coupled. In these systems, you have to take care of not only the logical and functional correctness of the application, you also have to take care of timing. And in many cases, these are critical applications like anything in automotive up to aerospace industry. But some things that are not that stringent in terms of criticality, like mobile applications, are also they also need complex development cycles. So for 20, 30 years now, 40 years, people said that the way of dealing with the complexity and heterogeneity of these complex physical systems was through the use of formal methods in software engineering. What do? We have a mathematical specifications for the system, and we use the mathematical results to do analysis of the designs. This is a main advantage of formal methods, and this is what we like from the formal methods. The formal methods are also provable. You can do analysis of properties and prove properties and correctness. They're reliable. This is another good advantage. It provides a common language to communicate in a team. Disadvantages are that most existing formal methods might be too complex to be useful, and demonstrations and proofs they become harder and harder when the design space scales up. There's explosion of states. There's constant work in this field, but it's still applicable to small parts of a complex physical system. Another main problem that most formal methods still have is that the techniques, they focus on software only. So you have a good model of the control system, but not of the controlled physical environment, okay? Other problem that we find it's important to deal with, these methods, as they're complex, the mathematical notations are good for applied mathematics and engineers, but when you need to deal with the business owners for decision making, it's hard to communicate. The existing methods are complicated for training and validation, and a lack of good visualization tools is a main factor on this. So, existing development methods are becoming better, but they're still not adequate for robust and designing optimal solutions. As we said, formal methods are hard to scale up, but something that we have seen in the field is that people use modeling and simulation instead. So instead of developing an application based on a formal mathematical specification and proofs, they get a semi-formal specification and they do simulations exhaustively to see how the system will behave, and then you get to gain some knowledge about the system. You get to know about the control system, the controlled system, the physical environment, and you get to build your application based on simulation. So in this case, instead of having a formal method, you start with your requirements and specifications, you conduct simulations, then you map your model to your hardware, you do prototyping, implementation, and fine-tuning and calibration, and you're good to go. But the key issue in this approach that it's used everywhere is what we call model continuity. The problem is that at this phase, everything that you have done, you throw away. So you get your engineers, you get your models built, your simulations constructed, conclusions taken about the system, and then somebody has to start building that. You start all from scratch all over again. So this model mapping, it's costly. You have to start the development from scratch using the knowledge that you have learned during this model and simulation phase. This is an expensive way of solving the problem, in particular if you're not General Motors. General Motors does that, right? So you, or I don't know, BMW, you are going to spend millions of dollars in modeling and simulation the control systems in your vehicle, because then you're going to sell thousands and thousands of cars that are very expensive, and you can distribute the cost of this phase, and you can have the luxury of throwing away the models. But if you're a startup, a small company, and you want to get more robust models that are more formal, it's hard to convince a manager to do any of these things. So what we have been investigating for years is how do we provide model continuity, okay? So I'm going to explain a methodology that we developed. It's ongoing. We have a lot of things that I will explain today. There are other things that we still need to work on. But the whole idea of the methodology is to use modeling and simulation as a base for engineering of the software development. The methodology allows you to integrate the applications, hardware, software, 3D visualization engines. We provide model continuity. We are centered in the model. The model is reused throughout the process. It's not only for learning and exploration. We model, we simulate, and the model that we use for simulate and for analysis goes to hardware without touching a line of code. So in the end, we claim that cost can be improved because you start building libraries of models that are reused, that are formally proved, and they're solid to be reused. You will see later, we have very practical reasons why we want advanced visualization facilities, including the application of the methodology for serious games and training. So the method is more or less like this. It's a tornado life cycle process. So the main cycle, it's over here. So you cycle over here, and you do tornado development in which you deliver products on every phase. You will start with the requirements of the control part of the real-time part of the cyber-physical system. And then you will have a requirements document, but then you also have the physical environment. This is reality, okay? You are going to embed this system into the real world. So you're going to do, imagine that you want to build a wireless ad hoc network in which the nodes are distributed in flying drones. So you have a drone network. So you form the drone network, and it's ad hoc. The drones fly for 45 minutes to 2 hours. Then they start switching them. It's dynamic, but then they have to fly. And in rain, it's raining, and in Arizona, it never rains. So you have a physical environment where this network is deployed. What do we do with it? We need to model the physical environment too. So in our case, we use a formal technique that's called Discrete Event System Specification. I will talk a few seconds about that later. I'm not going to explain devs here. If you're interested, we can talk about that later. But it's a formal method for discrete event systems that's generic. We have used devs for many things. In particular, we can use it for modeling the real-time controller and the physical part of the cyber-physical system. these models can be used for modeling, okay? We just abstract the simulation part and we focus on the model. The interesting part of this is that this real-time controller we can use through model checking engines, and we can check the certain properties in the model and work in the model world as long as we can. Ideally, if you can solve your problem here, you stop there. Why? Because the model properly checked will give you absolute knowledge about all of the properties of your controller with absolute precision. But normally there's an explosion of states, and there's only so much that you can check. So you can have a team of engineers working on model checking, and in parallel, you can use the same models to run modeling and simulation of the real-time controller. Why? Because both the model checking phase and the real-time controller phase are done with this DEVS formalism. You can also have in parallel another team of scientists, engineers, building models of the environment using the same methodology. So you have someone that using DEVS models the physical system, someone that models the controller. This can be simulated, this can be model checked. We cannot model check the world yet, okay? So there are some hybrid techniques that we have been using, but they're very limited. But so in the case of the ad hoc network and the flying drone, we could model the weather, we could model wind interaction with the drones through a complete physical system that is easily mixed with all of them. So we work in the model world, we do model checking, we do simulations of the real-time controller, we mix the real-time controller with the environment, we do testing of everything, and when we are becoming happy with components, we can deploy partially or completely components into a real-time DEVS executive that will use the same models to do the control, okay? Everything's model-centered. You deliver a version of the system, and you cycle through a next spiral again, and you start delivering better versions with higher functionality in every cycle. The interesting thing is that everything that you do here, it's the same always. We use the same model for that, and for that, without touching any of the components. Why we use DEVS? There are many reasons for that. One of the most interesting ones that I always share is, it's in this slide by my colleague, Hans van Geloof, who is now in Antwerp in Belgium. So during his PhD studies, he was doing multi-modeling analysis for a very concrete application. And then he did a very serious literature analysis, and he found out this series of relationships between modeling formalisms. As you can see, there are lots of arrows going to DEVS, which is what we use. And when you have an arrow, it means that somebody formally proved that you can do that with that. So this means that if you get state charts or Petri nets, you can do them with DEVS. Or you can have finite state automata done with DEVS, or finite state automata done as event scheduling with the discrete event, or event scheduling discrete event can be done as a finite state automata. But in 2000, something more interesting started to happen. So this side of the world is the discrete event side of the world, and this side of the world is the continuous system side of the world. So as you can see through model transformations, there are people that prove that, for instance, you can start with a causal bond graph and transform it into a DAE with causal sequence that can be represented with something that at that time was called DEVS and DES, which is a version of DEVS. So you can mix things like partial differential equation, bond graphs, Petri nets, and finite state automata using DEVS as a modeling assembly language. So we translate everything to DEVS, and we use DEVS to glue stuff, and this works beautifully. Something that it's even better is that this formalism evolved, and it has been improved a lot, and it has changed into something that is now a very well-defined formal numerical method for approximation of continuous systems. So now we can do devs for absolutely everything. So there are good approximations with bounded error, and you can mix continuous systems and discrete event systems seamlessly. What's the meaning of this? You have a team of people working. So let's take the drone example. You have the ad hoc network experts who know how to do, for instance, modeling in something like state charts or finite state automata, let's say. And there's someone in that group that knows how to study the concurrency of the ad hoc network, and they want to detect deadlocks using P-trinets. But then there is someone that knows how to model the PID controllers using bond graphs or, I don't know, or DAEs, okay? Nobody's going to learn. So the differential equation guys are not going to learn P-trinets. And the finite state automata people are not going to spend time learning state charts. Everybody has been living their 20 years of formal education plus work, becoming an expert in a field. You're not going to switch. So basically you get the best of each one of them, you put them in a room, and using devs you can glue things together, and this works really, really well. So we've been doing this with our methodology. So how do we, so let's go back to each one of, I'm going to explain now each one of the steps. The first step is we get the requirements of the real-time system, and then we write a real-time model using devs. We have a few languages for doing this. So we have something that looks like a finite state machine, a modified finite state machine, something that generates C++ code, something that generates C code. There are other versions that generate Python, etc. But this is how the model looks like. It has very well-defined semantics for the execution of each one of the components and coupling of components. And we've been working with this. So following this idea, we have done higher-level languages translated into devs. One that one of my students did like 15 years ago. He built a library of SAMS VHDL, converted into our CD++ devs tool, in which he got a VHDL design, converted into a dev simulation. If you have heard about Modelica, we were the first team in the world that built a Modelica compiler translated to devs. And it was a very nice experiment. That research stopped a long time ago, but we have a Modelica to devs translator in which you write your continuous system design in Modelica. We have a translator into devs and numerical methods related to devs, and you can run Modelica models. So in this phase, here you write things in Modelica, or a mix of between Modelica, P-trinets, devs, VHDL, and you can combine them together. But then the next phase is model checking. So what do we do for model checking? There has been a lot of research of model checking in devs, and this is another long story that if anybody wants to hear, we can explain later. But what our team did was we start with the devs design, and then we have proven behavioral equivalency between through B-simulation from a devs design and a time automata. And so we are able to get a devs design translated to time automata and get a well-established tool like UPAL or Kronos to do formal testing, formal verification using the time automata. And this formal verification, again, if you have many states, it can explode. But if it doesn't, you can get subsets of the specifications, subcomponents. Devs is modular, hierarchical. You can extract a part of it, send that to a time automata transformation and UPAL, and test that component exhaustively, and I don't know, prove properties like I don't know, deadlock freedom and correct operation, logical correctness, etc. That's one of the things that we do from the verification of model properties point of view. Something else that we've been working on is you get your components, and then you have to deploy this into processors, one or more processors, and then you get something like that that eventually get transformed into tasks that run into some kind of operating system, into or a supervisor running on a processor. So when we go from here to a processor with multiple instances of different tasks that conduct the actual work of your system, you end up having things like this, and you need to do schedulability analysis. So we came up with a mechanism to convert the high-level dev specification into task models, and we came up with mechanisms to study schedulability of this formally, and we came up with new methods to use imprecise computing and do schedulability computing, schedulability analysis of the imprecise computing models. So going back again, you start with your requirements for your real-time system, you conduct analysis, and you do your controller model. You can check the model, and you can assign it to task and study schedulability. There's people working on that. It takes a lot of time. It's complex to do, but in parallel, you get exactly the same model, and you put it to simulate, okay? It's the same model that we run for model checking and for simulation. We have an environment called CD++ that we use for modeling these devs models. So here's a devs couple model with components. There's a queue over there, and there's an atomic model, another couple model. And we can use all of the tools for simulation here and visualization. And so the current state, well, we use this simulation tool a lot. So I thought I would share one particular project with this crowd. This was done by one of my PhD students a few years ago already. When he started, he had a degree in electrical engineering, specialization in control systems, and he was working for Hewlett-Packard at the time. He was interested in networking and in queuing systems, and he came up with, well, he found a few interesting papers on how to represent a queuing system as a fluid flow using nonlinear approximations. And he got a few papers that were popular at that time. In particular, this slide is coming from this paper by Tipper and Sundaresan in 1990, in which the control engineers think that the queuing system is equivalent to, let's say, a plant in a control system where the network is the plant, and what you do is you use control theory to decide how many packets are you going to allow into or out the buffer. So instead of using traditional control methods for queuing, you use something like a control system, and you consider that now your buffer pool, it's like a vat in a manufacturing plant, and you open a valve, packets come, you open another valve, packets leave. So it's basically a traditional control system used for manufacturing plants, in which your control goal is not now keep the level of liquid in a vat stable. It's, for instance, I have quality of service requirements that I want to meet, and this is what you control. Your set point is your QoS requirement. So following our previous example, what we have done is, so this is the complete model. As you can see, there's the control part, okay? And there's one component over here that has been replaced by a discrete event. So this is a major advantage of devs. You can see that you can mix seamlessly continuous components, these integrators, with discrete event components. This is the control elements that are, so packets are discrete, right? So they're not continuous. So the control system tells you at how much speed can you take to receive new packets, but when the packets come are discrete. So this mix between continuous and discrete, it's a mess. It's seamless using devs, okay? It works beautifully, and yeah, we finished with the project around 2009. And after that, we also used the same set of tools. Oh, it seems that that one is automated and I forgot to. We had a long project with Ericsson Research in Ottawa, and initially they were interested in advancing for 5G mobile communications to get LTE advanced protocols and improve them somehow. And one of the techniques that they wanted to use, so coordinated multi-point comp, deals with user equipment that are at the edge of the cells using a synchronization mechanism. And the idea was, let's try to improve those mechanisms. We ended up with, between this project and the next one I will tell you in a second, with 6 patents with new algorithms for improving communication in comp. We did a couple of things with device-to-device communications, and finally heterogeneous networks, mixing nano and picocells with the basic base stations. And the idea is that the whole libraries of everything were built our dev simulator. All of the results are built using the methodology that I mentioned. I wanted to do experiments in the next phase that I will mention now, which is, let's put this into real hardware. But at that point, Ericsson says, no. In fact, they told us, we are interested in new protocols. We are not interested in the simulator because we have our own 1 million line of code simulator. That's the only thing that we're allowed to use inside the company to develop products and deploy. And my student spent an internship for 4 months over there, and they didn't let him get close to the simulator, not to the hardware, because there's competition. So Huawei is in Ottawa. Huawei has a relationship with our department. Half of the department professors are funded by Huawei. And when they first came to talk to me, they said something like, do you have anything to do with the H word, like a bad word, right? So the H word was Huawei. So as I have never done anything with Huawei, that were fighting for the leading position in the world at that time, they were able to collaborate with me, but half of my department couldn't even touch their stuff at that time because they're very secretive. It's all patented stuff, and it's a research division of Ericsson, and of course they are thinking 20 years in advance, and they don't want their patents to be leaked to competitors. So the next part, which is, let's get the model and deploy it into the real-time executive, we couldn't because we didn't have access to their base stations. Anyways, before the next part is dealt with, something else that I mentioned is that we can do very nicely is also to model the environment. So we use dev-based techniques for modeling the environment, and sometimes it takes really a lot of time to compute. We ended up building a couple of high-performance solutions. My students built parallel and distributed versions of our dev simulator. And in this one, so for instance, if you want to, so let's imagine right now there's an emergency scenario. The emergency scenario is there's a forest fire. And what are we going to do? We're going to deploy drones with a wireless ad hoc network to get information about what's going on, take pictures, send the information of the forest fire to the firefighters, and also provide communication in a fire area where the base stations are being destroyed by the catastrophe. And then we are going to build this, but we cannot burn a forest to test our drone solution. We can have a very precise simulation of the forest fire in high performance. We can get a geographical information system, get the map, deploy the forest fire model into the parallel simulation engine, and make it communicate with the real-time controllers that are controlling the drones in a seamless fashion. And we have done experiments with that. So A simple one that my student built was a prototype of artificial pancreas for people with diabetes. So she started by modeling the glucose cycle and simulating the glucose cycle exactly as I said before. And then she got a couple of sensors, and she was, releasing insulin. It was simulated because we cannot do experiments with humans, but the whole cycle was tested that way. Something else that we did was flow injection analysis, a set of experiments in which we inject a reactive and and water. They're mixed, and these people in the Department of Chemistry, they're interested in analyzing the particle interaction in this reactor. So we simulated the reactor because the reactive is extremely expensive, and so we can do the software part of the controller that will release the chemical components into the reactor, simulate it, and then deploy. If you go to my YouTube website, you will see lots of experiments in robotics, basically because it's good for undergrad students to test the methodology, and it's visual, it's nice, they get excited. But for instance, here you have an EPAC that's communicating in real time with a model of a physical system that will tell what's going on in the environment, and the robot is reacting to the environment. The environment does not exist. It's a virtual environment, and we have visualization engines to see what's going on. So we are at this point in which you get the requirements, you get the controller, you model check the controller, you get your environment, your forest fire, and you can simulate your forest fire, and this model can be simulated. This simulator can talk to the simulator in no time. But then we have to deploy it into the actual platform. We have an embedded version of our simulator that is improving every day. We started having a Xenomai-based real-time version of our CD++ tool. Now we got rid of Xenomai, and we are having devs-only models running on bare hardware. So the system design is still done with devs. We study behavior and structure through simulation. We do formal timing specification and analysis, and then we move it to the hardware, and the hardware basically, the only non-dev things that we use are the drivers. So we got a library of drivers because we don't want to spend time coding a dev's version of, a motor or a light sensor. There are good libraries for that. So we use the drivers from libraries. Everything else is a dev's model. We have deployed this in different platforms just to test the concept, and we had one FPGA board a few years ago. We have a bunch on ARM-based microcontrollers, and our robotic applications would more or less look like that. You will start with a dev's model that it's a couple model, it's a structural model that will tell you how your components interact, and then you will say each one of them, what do they do in terms of a dev's state machine, and then you can implement that. This gets converted into a C version of this state machine that executes. We have mapping of the input-output ports, and then we have the robot up and running in no time. We have third and fourth year undergrad students working with this methodology. This is not top-level PhD complicated stuff done. We have brought already, so the PhD students, they take care of everything that's under the hood, which is all of the formal techniques that allow you to do this and that, and they make it, the master students program it to make it happen, and then the undergrad students use it for assignments. So let me show you the continuation of that control system-based algorithms for packet control that I discussed earlier. So what my student did at that time was to use an Intel IXP 2400, which is a network processing unit. It's a board that we got a donation. It looks like that. And the idea is that you can build, so you see the optical input-output there. You can build this to build high-speed optical networks. It was one of the first existing multi-core processors. This was done a while ago. And it has a SIMD set of micro engines that they can packetize, and they packetize very quickly whatever you want to transmit or receive. So as you can see, what we have done is we have put our CD++ embedded simulator as the core components running on an X-scale core, and then components of the library into the micro program, into the micro blocks of the micro engines. Okay, and as a test case scenario, my student was again interested in hybrid control models. We started with this existing nonlinear approximation from the paper I mentioned earlier. We built a dev specification for that and ran simulations. And as this is a continuous model specification, we got almost perfect results, very good approximation. So this is the Q length at a certain point. This is the control signal, and the reference signal, this is the set point. And by fine-tuning the control system parameters, we get to maintain the number of packets controlled. But then we need to deploy this into the hardware, so we did a devs version using a discretized PI controller that uses forward Euler that is converted into a devs specification. It's done naturally in devs. There's no approximation. There's this method called quantized taste systems that will have an equivalent version of forward Euler made as a devs model. And there was some verification required to adjust the sample period, but in the end, we ended up having the same model, and we replaced a continuous component, the PI controller, by a discrete event version of the controller using quantized state systems. So as you can see here, we have an integral, okay, that is replaced by a quantized component, which is discrete. And we have a discretized version that does exactly the same as the continuous version, without worrying too much about anything, right? So it's the same high-level model, and integration between the most interesting part for us was this. All of these are continuous, all of these are continuous components, okay? This is still a continuous component. This is still a continuous component. But this one, it's a discrete event component. And they mix beautifully because we translate through devs as Hans's multiple arrow formalism showed earlier. We built a test bed with a couple of these optical network boards. We connected a traffic analyzer. We deployed, as we explained earlier, the protocols that were defined, conducted a few tests, and the whole point here was to test the methodology, not the algorithms. So in summary, after you are done with the model checking and the simulation, you deploy it into the executive, and the same model is used for everything. Now, the next step that we need to consider is validation and also, if you wish, training. Once you're done with and during the process of analysis and development and deployment and implementation, you need to talk to your customers, right? And at a certain point, these were our customers. So that's all fake, okay? So there's only a part of the whole thing, which is the altar that still exists. It's in a museum. It's a church that burned down, and we started collaborating with the people at the School of Architecture years ago because they were doing reconstruction of 3D historical places. And so we wanted to work with them because this is super exciting. We have no clue about about how to do any of this. But they would go to a historical site with a laser scanner. They would get millions of points. They would convert that into a 3D model, and they would overimpose photographies, and they would complete what's missing with their own invention and creativity, because they can draw stuff. And so we started working with them. And for them, a model is, so we will get this room, and we will get to know where the chairs are and where to put the lightings, and those have blinds, and there's heating, and there's a microphone, and there's light that's very hot. But for us, we don't care only about that. We also care about dynamics. So second project that we collaborated with them was they modeled the whole downtown Montreal area for heritage purposes, and they had 3D models of the area, and we started putting people. We started doing crowd dynamics analysis on the area. That's where all of the festivals happen. If you ever go on a plane and you see Just for Laughs, and there's well, it's filmed over there, okay? And it's changing a lot. So Heritage Canada wanted to have a version of how the neighborhood looks like for the future generations, because this is the place where all of the immigrants landed in around 1880. When they opened immigration, this is places where they used to live, and the main offices of the immigration agencies were there, and it's all being changed every day, okay? So heritage purposes, one. Second, I want people walking around. I want to see what happens if you have a festival with 60,000 people walking around the area, and there is an emergency and people start running. So we started working with them, and what they do is they give us a BIM model of it's a 3D version of a building with a database associated that tells you everything about the building, okay? So we've been working with them for a long time. We did things like evacuation and occupation of buildings, and we had a project with a company in which we studied the flow of pedestrians into a corridor downtown, because there's a new train that's being built, and in the winter people would get into the buildings to avoid the cold. And so mixing 3D buildings with BIM specifications and pedestrian modeling. And this ended up in our current project, which is called Sustain. So as you can see, so this is a BIM version of the Carleton University campus. Okay, these are all of the buildings in the campus. This is a geographical information system representation of downtown New York City, the Central Park over there. And this is an actual building. This is the School of Architecture, and they're building a building over there. So what are we doing? What's the point of all of this? It's still the same thing, okay? So I will explain in a second what are the control systems that we're deploying. But here, what I'm showing you is the environment and the model that we are building for visualization and training purposes, okay? We get to see the students moving around campus, okay? Or in this particular case, they're building this new building, and the architects are really upset because this is a heritage building. It's supposed to be one of the top 10 School of Architecture buildings in the world in terms of not the beauty, the quality of usage for schools of architecture. It's a landmark Canadian building, and they're putting the School of Business in front of it. And so it has many things. It has big spaces for design, so they meet and they discuss, and they have all of the right spaces distributed in the right way with natural lighting, and since the 60s. And now they put a big building, and using our methodology, what the student is doing is, let's see how is this going to affect lighting. So that's one thing, but what's the relationship with MASCOTS? Well, it's called Sustain because we want to improve sustainability of the buildings. And there are, in particular, 2 buildings on campus that were built very recently that they are all equipped with electronics and control systems. They're all wired, and we can use them as a live lab. So we have all of the data of the buildings. In particular, we're interested in who is there and when. Why is that? Because what we want to do is to reduce emissions of buildings. So Errol was talking about the better use of energy for networks, and the reality is that 40% of the carbon emissions in the world come from buildings. So this is real data. So it's not vehicles. Vehicles is 20%. We are very worried about vehicles because we see them. We see the smoke and it looks disgusting, and we can clearly see them. We don't see that our house is, well, the water heater in our house is worse than a car, okay? And there are lots of houses with water heaters in developed countries. So 40% of emissions in the world. New York City, 80% of the emissions are buildings. So there's a lot of work all over the world. In Europe, it's well advanced to have zero emission buildings. So what we are doing is we work with Autodesk Research, which are the guys who do the software for BIM. And they have incorporated a devs simulator in their tools, but we want to do the next step, which is you design the building, we use the building for simulation, we use the control systems in the building, as I explained earlier, we do the control systems for the heating in a room using this devs methodology, we can do model checking, we have the controller, we deploy the controller, and then we can do interaction of the control system and a visualization. We can highlight which building is misusing energy, because the architects can do fancy ways of that. There are advanced tools for analysis of the energy consumption of the building that we're working with them to deal with. We're integrating that at a larger area, the geographical regional level. But one of the things that we want to do is, so a major aspect here is heating and air conditioning are major components of emission. And so right now, that room where we eat, it's empty, and it's still heated. And there's lights there, okay? And there are lots of offices, there's nobody using them. And there are many factors. It's like people interact with the building that they call the envelope in different ways. So you come here and start touching stuff, and you are going to change the heating. So you're going to pump up the heating and open the window. And then you're going to close the blinds because it reflects on your laptop and turn on the lights. All of these automated systems will try to automate how the building works to reduce energy consumption, but then we have the humans in there that we have to study. So we're using all of this methodology to study all of these aspects. The project is just starting, so it's only 1 year old, so we don't have exciting results yet. The most exciting result is related to this conference, which is we have invented a mechanism for detecting, for approximating who is where through the use of your Wi-Fi connection. So it's a very good estimation of who is in a room and doing what, because you got connected to your Wi-Fi. So you are using the network in the building to detect occupancy, and the models that we built for that, of course, they are all anonymized because we don't know your IP. We know that you are connected. Maybe there are errors because you might be connected and you might have gone to have a cup of coffee and still be connected. But through this work with the team and the civil engineers, they invented a way of good approximation of occupancy of the rooms, which is pretty promising. So we are using all of the methodology for that. Oop. Next. So how much time do I have? 15 minutes. I will be done in 5. I can show you videos anyways. So yes. So in summary, you get your real-time control requirements, you get your physical environment, you can model the environment and the real-time control. The controller can be checked formally using a model checking engine. If this takes too long, we can simulate what the model does. And once we are happy, this simulation model can interact with the environment model nicely. And once we are happy, we deploy that into an executive. And we do, we call this the model-based engineering for software development. We can mix a variety of hardware, a variety of software, and 3D visualization. We reuse the models throughout the process, so the cost is improved. We have a collaborative environment for development, advanced visualization facilities. And what we can do is, I can show you a couple of videos, but let me, I skipped these ones because I thought it was going to take me a long time, because it normally does, but people are in general interested on what is this devs thing. So I'm going to explain in 10 minutes the general ideas of what this devs formalism is. And a devs model is a discrete event model, okay? We focus on the modeling aspects of the system. The simulator is completely separated from the model, so there is a simulation engine that runs a simulation algorithm that was formally proved that executes these things correctly. This has been going on since 1970s, so the first algorithms were proven a long time ago, and this has evolved a lot to include many different kinds of specifications. But a model more or less works as follows. Two kinds of models. It's based on theory of dynamic systems. So it's a version of system theory, okay? In which you have black boxes, white boxes. Black boxes represent behavior, white boxes represent structure. The structural models do not include behavior. The behavioral models know nothing about structure. So this is the general aspect of the black box, the behavioral model, which we call anatomic model. And so some people get scared, not in this community, but the people without a lot. So we convert this into fancy pictures and videos because there are people that do not understand the mathematics behind that. So we hide it. We give friendly user interfaces so they can use it, and then you will get the computer experts to code interesting stuff and the theoreticians to work on theory of this, but we hide all of this stuff from the non-experts, okay? But what we do behind, behind the scenes is to define atomic and coupled models. An atomic model that some people get scared of, it's a composition of 3 sets over here and 5 functions, okay? So anything that you can do is defined in these functions, and these functions can only act on these sets. So at a certain point, any model, atomic or coupled, is at a given state S, okay? And the state S is kept during a duration of the state defined by the time advance of that state. So, very simple example. How much time do I have left? 5 minutes. So the state of this room is, there's one person talking and 30 sitting for 5 minutes. So that's the state. The state is not 20 plus 1. It's 30 plus 1. It's 30 plus 1 for 5 minutes. And as soon as I have said for 5 minutes, it's not 5 minutes anymore, right? Because it's a discrete event specification and time is continuous and it has already changed. But I don't care. Because the only thing I care about is meaningful events. So if I care about something that happens here, for instance, I drop a microphone, it's not 5 minutes. It's, well, he's going to drop the microphone in 1 minute, so I should record that 1 minute. But right now, the only meaningful event is that in 5 minutes, we're going for coffee. So, yeah. So how do you program TA of S? Well, you do an increasing boredom divided by caffeine lack function that says, when time passes, I get more anxious. And in 5 minutes, I need coffee, okay? Good. So I only care about 5 minutes. At that time, the event, the next meaningful event, which is called the imminent event, is going to happen. And when it happens, 2 things happen at the same time. Number one, we generate an output. As you can see, the output is an output of the state of the room. Here is where you define what you want to send out from the room. We could send many things. Gender balance in telecommunication. We count how many ladies and gentlemen, and that's what we output. Temperature in the room. We get a sensor and we say, okay, there's 30 people and we have the heating up. This is what we do in our project. And we should reduce the heating level because it's not that cold. We are here right now. And if there's more people, less. So the output could be the temperature. It could be, I don't know, you're in the business school. Average salary in the room. Age. Oh, I'm becoming politically incorrect. Anyways, so you take whatever you want and you send it out. This is the main aspect of your model. This is where you work, okay? The only important thing is that this output should generate values that belong to the set Y. It's a bag of outputs YB. So for instance, if things that could happen, you have a very good model of occupancy of people in rooms, and then you get hired to do agricultural modeling, and you say, oh, the people in this room, it's very similar to the sheep in that field. We are locked. Sometimes they open the gate. We go for coffee. They go for grass feeding. But in terms of occupancy of an area, it's the same, right? So we have a company. We sell the service to the agricultural company, and we're going to reuse what we use for this building. But then we forget that now this should be sheep. So the formal specification will tell you, as soon as you say, these are sheep, and you see people over here, there's something wrong, and the specification will tell you, no, careful, there's something that you have to fix, and it's probably here. So it gives you hints on where do you look for the errors, and doing testing and fixing the errors is more or less seamless and trivial. Once you have done that, we do something what we call the internal state. Something important is that you can generate empty outputs. So sometimes you don't generate anything. But as soon as you are done with this, you produce an internal state. So you say, coffee time, there were 30 people, one talking. Now, he shut up, we're gone. So what's the state of the room? The room is empty. And this becomes the state of the model. But as we say, the state, it's a pair. It's not a value. It's not 0 people. It's 0 people, and for how long? One interesting thing that Dev has is you can include infinity as for how long. You can make a model passive by saying, we are going to leave this room forever. Okay? What would be the case? It's not coffee time. There's a fire alarm. And they evacuate the building, and they close it forever, right? We can never come back. So how do we represent that? The time advance is infinity. This is very important because it's a termination condition for the simulator algorithm. If all of your models have time advance infinity, there's nothing else to do, finish your simulation. Okay? Good. So, but you can also have the schedule. So we have MASCOTS, and the next thing that will happen is after the coffee break, which is half an hour later. So it's empty for 20 minutes. In 20 minutes, we will say there was no one over there. Change to the next state. The next state is there should be flashing lights, 1 second flash, another second flash, another second flash, until somebody shows up. When somebody shows up, this is what happens. So we were waiting for 2 minutes, and everybody's still having coffee. And then people start showing up. So the first person comes. These should be persons, not sheep. So also I can check that this input value corresponds to this set for formal verification. And in that case, what we do is get the current state, which is the room is empty, get the elapsed time, 2 minutes have been elapsed, get the input, and do something with it. It's a function, okay? So you can use these 3 variables to do whatever you want. As you can see, this is pretty interesting because you can do stuff with the elapsed time. You can react. This is good for communication protocols, okay? So you have timeout. You're in the middle of a timeout. How much time has been elapsed since I sent the packet? 1 millisecond. Oh, okay, we're good. or 10 milliseconds, you're not good. You should have been resending something else before. So send a negative acknowledgement because your packet, your acknowledgement has arrived after 10 milliseconds. So this one keeps the track of the current model, okay? And you compute that, and this goes like that forever. There's an elegant way of dealing with conflicts. Sometimes what happens is this: you have outputs simultaneously with the inputs. So you said, right now, it's the time for me to send a packet. And simultaneously, another packet arrives. What do I do first? Do I send the packet out, or do I receive the packet and put it in the queue? Well, if my buffer is full, if I take the packet first, it will be rejected because there's no room. But if I take the output first and I empty some space in the buffer, there's no bounce. And this is a major design decision. You want to do it in different ways according to your needs. Well, you do it in another function which is called the confluent function that deals with simultaneous events. Yeah. So, now that you know everything about devs, feel free to check our videos in our YouTube channel. Get in touch with me if you need anything, and thank you very much.
First, thank you very much for your talk. I get a question about what you have done with BIM and all the building simulation, etc. Do you find sometimes some constraints that could not be easily simulated using finished state machine with your formalism? Or so my question is, sometimes, for example, when you want to simulate people that move, in a way, is it easy to do, or do you have to really build complex model for having a precise simulation on that?
So you can do the two. Okay, so if you're happy with rapid prototyping and a simple model that does very basic stuff, you can do that. If you want to become refined, you can become super refined. One of the things that I didn't show in the videos that I wanted to, because it doesn't have much to do with this crowd, we've been working on crowd modeling. So crowd modeling, we started with very simple models in which we split the space in cells, and we say, okay, the cell in front of you is empty, walk. And if it's full, walk to the left or walk to the right, do sidestepping. But we ended up with a very fancy model of pedestrian in which we are able to run 100,000 pedestrians with collision avoidance mechanism and lane formation, use a model that my student created, inspired on how our amygdala works, and personal space management. So basically what the model does is what we humans do, which is we want to keep our space. And it's different in different cultures. That can be incorporated into the model. It's a parameter for the pedestrian model, and you keep. So if I'm going to walk against this, I'm going to avoid it. That's collision avoidance. But if I walk against in his direction, it seems that our brain reacts to unknown people as it would react to, let's say, a lion. And we try to avoid conflict. And we try to steer away from people. It's different when you know the person, okay? So we run thousands of different simulations, and we ended up with super exciting emergent behavior, like bidirectional flows formed automatically without programming anything. If you see what the animators do, they spend lots of time doing programming of the bidirectional flows. It happens naturally in our model. And it was all done through evolution of simple models into something more complex. You can start simple and make it more and more complex. Everything's reusable. You put it into a database, someone else uses it, does something more complicated, and then you build on it without much complication. Yeah.
So, thank you for your presentation.
What I understood is that you aggregate different types of models into your model, and you have your tool for running simulations, right? So my question is, according to the domain you're working on, you have really state-of-the-art tools. For instance, when using scheduling for real-time systems, you have a couple of 3, 4 really well-known simulators. So my question is, how do you interface with such tools? And is it not that difficult to maintain those interfaces with so many different domain tools for your own? Because I've seen that you developed your own tools also. So how do you manage this this interoperability between these different tools?
This question was a major question in modeling and simulation in the 90s. They started asking this question, and it became a major research area in the field, and it was driven by initially the Department of Defense in the United States, that they were more worried not about scheduling tools or NS2 or OpenNet. They were interested about, we have a tank simulator that costed $20 million. And then we have a jet fighter simulator that costed $35 million. And we have a vessel, ship simulator that costed $40 million. And now we want to do exercises all together, because the Navy, the Army, and the Air Force, they were training their pilots and their fighters in their own machines. And eventually they said, oh, we need to put all of them together. And but then they say, well, but the Navy simulators are in New Jersey, and the jet fighters are in Arizona, and the tanks are in California. I don't care. Here you have $20 billion. Make it work. That's how it started. Okay. So they started working in distributed simulation protocols driven by that. It ended up being an IEEE standard called the high-level architecture. And supposedly, this was going to solve the problem, but it didn't. The people that put the money on the table recognized 10, 15 years later that was a failed $20 billion experiment. There are things that work really nicely, okay? So you can interoperate simulators. But the main problem is that this was attacked at the level of the simulator, not at the level of the model. So I didn't say a word about the simulator and how this is simulated. But the HLA provide an API to hook up your simulator. So your simulator should be adapted to HLA and provide input-output ports, let's call them, to talk to the HLA. And then you can make simulator A talk to simulator B. But they don't understand each other at the semantic level. They might understand the bits that are transferred for the simulator to one to the other, but what the model mean, it's not understandable. And that's where the main problem is. So we have been doing, so how do we do it? We only do it when we have a project in which we need it. So we have done it with BIM tools because we have a project with Autodesk, and we have done it with geographical information systems because that's something, I have a couple of students that are experts in GIS and they wanted to do it, and we have an open source tool to work with that, and we do it. But one of the main devs experts in the world, he's from Korea, Tak-Gon Kim, his research was funded by defense in Korea. His research was on many different fields, but what he built was something that he called the devs bus. You have the HLA as the lower layer, and he hid the lower layer with devs. So all of the inconsistencies of the HLA are not there anymore because he puts a devs wrapper on top of the HLA, and that wrapper understands a tool that you have above that. So his own dev simulator, like ours, System C, MATLAB Simulink, all working together through a devs interface in the HLA. and he has dozens of other tools, and probably he has others that he cannot tell about because it's defense related. It works really nice. Basically, you need the tool to provide you with an API to communicate with the outside world. Of course, if it's closed, you will not be able to do anything. But if you have the API, connecting through a devs wrapper, it's something that works nicely. We've been doing that since, I don't know, 2002. And some other people have done it even more successfully and in a very elegant way. They have formally specified how to do it. They have even defined a meta language with all of the semantics on how to construct those wrappers, and it works really nice. Thanks again for the